carbonyl compounds. So carbonyl compounds include aldehydes and ketones. So an aldehyde has a functional group like this, where you've got your carbonyl group, the COO, you've got an R group on one side, and you've got a hydrogen on the other. A ketone, on the other hand, will have the same carbonyl group, but two R groups either side. So this carbonyl group could be seen in the middle of a molecule. Naming aldehydes. So let's take, for example, propanal. So first of all, let's use the prefix prop, and that shows we've got 3 carbons. Our AN shows that we've got our carbon-carbon single bonds, and then our AL shows that we've got an aldehyde functional group. So therefore we know it will look like this. Our 3 carbons is our longest chain, single bonds, and our aldehyde functional group here. Naming ketones. Let's take propanone here. So again, 3 carbons, single bonds, and then our ketone functional group. So that's breaking down that word, and from that we can find out this is the structure of propanone. 3 carbons, single bonds between carbon, and then we've got our ketone. As you can see, this would represent one R group, and this would represent the second. Physical properties. So the intermolecular forces in carbonyl compounds. So they have permanent dipole. So this sets up our delta positive on our carbon, delta negative oxygen. They have London forces because they have electrons, but they do not exhibit hydrogen bonding because there's not hydrogen directly bonded to an F, an O, or an N. Boiling points. So aldehydes and ketones have higher boiling points than the corresponding alkanes, and this is because they have more electrons, so they have stronger London forces, and then also permanent dipole. But in this situation, London is most important. They have lower boiling points than the corresponding alcohols, and this is because they don't exhibit hydrogen bonding, which is the strongest type of intermolecular force. Solubility. So just draw a little diagram for solubility. So it will hydrogen bond because let's take, for example, this ketone here. So we've got our ketone here, and we'll have our water molecule here. And so they will hydrogen bond because the carbon from the carbonyl compound will make sure that the carbonyl compound provides the oxygen, whereas the water provides the hydrogen. So they're soluble in water because this is delta negative, and this is delta positive, and this is delta negative, and that allows our hydrogen bonding between these molecules. But as chain length increases, so this is quite a short chain molecule, but as chain length increases, the solubility decreases. So, for example, this molecule would be soluble in water, but with increasing chain length, will not be soluble. And that's because this is going to have more non-polar characteristics because of this long hydrocarbon chain. So let's go into the reactions of carbonyl compounds. So firstly, the nucleophilic addition with HCN in the presence of KCN. So let's just quickly go over what a nucleophile is. And that's a species with a lone pair of electrons, so it's attracted to a nucleus where there's protons. Because obviously electrons are negatively charged, protons are positively charged. A Addition is one or more groups added to give a single product. So let's have a look. So it makes an hydroxynitrile. So that means there's an OH group and a CN group. It's important that it increases the carbon chain by 1 because you're adding a CN, which obviously increases the carbon chain. So let's go over a quick example. So let's take butanone. Okay, this is obviously saturated with hydrogens, and we can add HCN, and what we see is, oops, we'll just saturate this one with so our final product will have an OH group here, and we'll have a C triple bond N on this side here. Obviously that's full of hydrogen too. So the effect of pH on this reaction, if the pH is too low, then there's not enough CN minus ions, but if the pH is too high, so more alkaline, then we've got not enough H plus ions, meaning that the reaction wouldn't go. So let's have a look at the mechanism for this reaction. So if we take here an aldehyde, it's a bit sharp. So the reaction occurs in 2 steps. So this is the nucleophilic addition, so we need to have our nucleophile, which in this instance, in step 1, is a CN minus, but this here is from the KCN, so that's why it has to be in the presence of KCN in order to start this reaction. So this has got a double bond, sorry, this has got a lone pair of electrons here, and this is going to effectively, oh oops, I've missed the addition, and that's going to pop this bond here, which is delta positive, and the oxygen is delta negative, and therefore we're going to get this double bond being broken here, and that's going to lead us to make this, which is in between the steps, and what we have is this CN group, this cyanide group, attaching, and now we've got a full positive oxygen because it's gained a pair of electrons from this bond here. So this will break apart a HCN because it's fully negative, and that's how we get our step 2 of this reaction, where we take our product from the first stage and what we can see, as we've got a lone pair here, we can see this attacking a HCN, just represent like this, which is So it attacks our hydrogen, pops this bond, and therefore we get our final product, which will have both our OH group on and our cyanide group on, making our hydroxynitrile. So let's go into the hydrolysis of the CN group. So this is if the nitrile group is further reacted with HCl and H2O, the nitrile group can be hydrolyzed to a carboxylic acid. So let's take a nitrile. So let's represent the nitrile group here. And once again, notice that you've extended the carbon chain. And then we're going to add. Then we're going to add HCl and H2O, and we can form our carboxylic acid, which will have functional group like this. So let's see the reaction with LiAlH4 in dry ether. So if you can remember that this is a reducing agent, because this is a reduction reaction here, and that it can be represented with the square brackets in the H. So if you remember back to the oxidation of alcohols, this is the opposite. So if you remember going from primary alcohols to aldehydes to carboxylic acids, or secondary alcohols to ketones, and then they can't be oxidized further. If you can't remember that, feel free to go back to the alcohols video. So you can use this reducing agent in dry ether, which is a source of H- ions, and it has to be dry because you can't have any water, and you can actually bring the carbonyl compound back into the alcohol. And it won't reduce C's double bond C and the single bond, as won't attack electron-rich area. So with 2,4-dinitrophenylhydrazine, or 2,4-DMPH, it can be used as a qualitative test for carbonyl groups, so aldehydes and ketones, because it's only testing for this group. So you'll see a yellow and / orange precipitate being formed if it's a positive result, and that indicates an aldehyde or ketone present. So it's a condensation reaction as two molecules bond together to form a bigger molecule with the elimination of a water. So next reaction is with Felling's solution, which is an oxidation reaction. And This can be used as a quality test for aldehydes, but only aldehydes. It will not give a positive test for ketones. So it's a good way if you want to tell the difference between an aldehyde and a ketone. So oxidation will turn the aldehyde to a salt of the carboxylic acid. You just add a few drops and warm it in a hot water bath. Positive result indicating our aldehyde will be a red precipitate. And this is because the complex copper 2 ions are reduced by the aldehyde to copper 1 oxide. So effectively we get this colour change through here. So we've got our aldehyde, and we've got our colour change, you can see. So this is similar to with Benedict's solution, where effectively the same reaction takes place with these copper ions being reduced. So this will again only work for aldehydes. The only difference is that the copper 2 ions are complexed with different compounds, but they both oxidize aldehydes and reduce Cu2+ ions, so we'll give the same result. So with Tollin's reagent, this is another qualitative test for aldehydes. So again, to tell the difference, and it's also known as the silver mirror test. So it's an oxidation reaction, and it turns the aldehydes to salt of carboxylic acid again. And this is done by aqueous silver nitrate being mixed with aqueous sodium hydroxide. Then you add aqueous ammonia dropwise until the precipitated silver oxide completely dissolves. So the positive result is a silver mirror. So that will look a lot like this inside your test tube. And that indicates an aldehyde is present. And this is because our Ag+ ions in aqueous are being reduced by the aldehyde again to form Ag salt. That's where we get our silver mirror formed. And that's the overall reaction with an aldehyde, forming our salt. With potassium dichromate and sulfuric acid, so this can be used as a qualitative test for aldehydes again, and it's another oxidation reaction, and it's the same as the secondary oxidation of primary alcohols, if you can remember back when we were using potassium dichromate again. So acidified potassium dichromate is a strong oxidizing agent, so it can turn the aldehyde to a carboxylic acid, and this can be represented in equations as this square bracket O, because it's an oxidizing agent. So our positive result will be a colour change from orange to green. And that's the reaction there. And remember, this will only work for aldehydes. Finally, their reaction with iodine in the presence of an alkali. This is also known as the iodoform test, and it identifies a CH3C double bond O group, but also a CH3CHO OH group. So the positive test will be the yellow iodoform produced. So they all have a methyl group adjacent to a carbon with an oxygen or an OH group. So we have our methyl group adjacent to carbon and an oxygen, our methyl group adjacent to our OH group. So examples of these would be ethanol, again methyl group and our OH, ethanal, which is, so we've got an alcohol, an aldehyde, then also a methyl ketone. So example would be ethanol, and here we see the reaction taking place, iodine in the presence of our sodium hydroxide, which is acting as our alkali, and there we produce our yellow iodoform, which shows us our positive test.